All right, we'll continue with finally the solution to our boundary value problem, right? And just to get us all back onto the same slide, so to speak, recall that we are trying to solve the flow of an incompressible viscous fluid, right, at steady state. And of course, we made a few more assumptions along the way, okay? So, the story so far. Okay. The key ingredients are that for the pressure, we have the pressure is a function of x3 alone, and for the velocity, v, we've seen that it has the form 0, 0, and for the v3 component, we have a function which is a function of x1 and x2. Okay? And now, the PDE we need to solve is this. Partial of p with respect to x3 plus mu partial of chi, second derivative of chi with respect to x1 square plus second derivative of chi with respect to x2 square. Okay? This is equal to 0. Okay? This, by the way, represents the Laplacian of chi in the E1, E2 plane. Okay? So that's something that we may write as del bar chi, del bar square chi. Okay? Where del bar is our Laplacian operator, okay, restricted to 2 dimensions. Right? Okay? All right. Let me rewrite this equation. Okay? So this equation is of the form partial of p with respect to x3 equals minus mu. Let me use what I just introduced here, del bar square of chi. Okay? I want to make a certain argument here, and to make that argument, let me remind ourselves of the parametrizations here. Okay, you observe that on the left-hand side, we have something that depends only on x3, whereas on the right-hand side, we have something that depends only on x1 and x2. Okay, yet they must always be equal. Okay, they must be equal at every point in the domain. The only way this can happen is if each of them is some g which is a constant. Okay? Right? And the reason is that this depends on x3 and this depends on x1 and x2 only. Okay? So the only way that can work out is if each of them is equal to a constant. All right, that really makes our life very easy, because separately that implies that partial of p with respect to x3 equals g, okay, which implies that then for p we have the form p equals g times x3 plus, let's say, g0, some constant, some other constant, okay, and this is p as a function of x3. But now we invoke our boundary conditions for p, okay. So the boundary conditions on p, okay, they were that p at x3 equals 0 equals P0, the inlet pressure, okay, right. What this implies for us then is that G0 is P0, right, and P at x3 equals P at the outlet, which we had denoted as P sub L, okay, as our boundary condition. And this then implies for us that G times L plus P0 equals P sub L, okay. So very simply, G is the pressure gradient PL minus P0 divided by L, okay, and our pressure as a function of position. Remember, the flow is steady, so there is no dependence on time here. This is PL minus P0 divided by L times x3 plus P0, okay. We've got our solution for P, all right. Okay, let's turn to the Laplacian. Del bar chi equals g, right, which was the second, which is essentially the right-hand side of our equation. Sorry, it's not just this. It was, I think it was mu del bar square chi equals 0, equals g, okay. Now, remember that the conditions we have here are the following. Okay, now let's talk about the boundary conditions on the velocity. Okay, those boundary conditions were that v equals 0 at x1 square plus x2 square equals a square. Okay. Now, and then we also saw that, but then we also know that v1 and v2 are equal to 0. v1 and v2 we've assumed are equal to 0. Okay, so really this implies that the boundary condition really applies to v3, right? It's the only one left in the game. Okay, and in particular we have v3 at x1 square plus x2 square equals a square. That has to be equal to 0. Okay, but then remember that v3 is just chi. Okay, that's what we have in this equation on the top. So what all of this means is that we need to pick a function chi which is such that it vanishes at the walls, right, and satisfies that, essentially satisfies the Poisson equation that we have here. This equation, by the way, is called the Poisson equation. Okay, that form is called the Poisson equation. Okay, easy enough. consider chi of x1 comma x2 equals a square minus x1 square minus x2 square. A very famous and living applied mathematician said that the best way to find the solution of a PDE is to know the solution, right? So we know the solution of this form, right? So we use it here. Okay, you see that it basically works in there now when we make, you see that this satisfies the boundary condition automatically, right? So we see that chi at x1 squared plus x2 squared equals a square equals 0, right? So it satisfies the boundary condition. Okay, so this thing satisfies the boundary condition. Okay, let's see what happens when we plug it back into our PDE. So plug it back into our PDE, which is the Poisson equation. Okay, which is minus mu del bar square chi equals g. Okay, this implies now that minus mu. Now, if you remember what we had in the previous slide for chi, you apply del bar square to it, you basically get minus 4. Okay, equals g, and this is because del bar square of chi equals del square del x1 square plus del square del x2 square applied to a square minus x1 square minus x2 square. Okay? Okay, so you get minus 4. Okay, so what we're seeing here is that, okay, so we're seeing that, oh, okay, I see, I took too special a form for chi. Let's do the following. Okay, the form for chi that I have can also be extended. Let me do it right here. Okay, note that chi can simply be written also as some other constant a times the form that we took. Right? Because any such form, a multiplied by this, right? Right? For any constant a, right? For any constant a belongs to R. Right? This also satisfies the boundary condition. Okay, and then if we plug it back into our differential equation, a will stay in the game, and you'll see why I needed to have a in the game as well. Okay, so let me just state this. Note that chi equals this form also satisfies the boundary condition. Okay, and now when we make the substitution for this form of chi in our Poisson equation at the top of this slide, what we get is minus mu times a times minus 4 equals g. Okay, the reason I needed to put back an a in there is because I realized that, well, mu is specified, it's a parameter in that specifies the PDE. It's the viscosity coefficient. We already derived what g was in terms of the boundary conditions on the pressure. So we need another. We needed another constant. Otherwise, we would be saying that mu is always equal to g. You know, mu is a function of g always, right? Or that it's a very particular function of g. Okay, which we don't want. All right. Because that sort of overspecifies the problem, right? And the difficulty was that we assumed a particular form of the many that satisfy the boundary condition. Okay, so that's actually a useful exercise. It was not a planned error, but it's a useful exercise to realize how you actually need to construct solutions to PDEs, right? You need to leave enough flexibility to satisfy all the conditions. All right, anyway, what this implies then is that we have for A equals g over 4 mu. Okay, and finally, we have then for our velocity, v3, function of x1 and x2, we have g over 4 mu, okay, times a square minus x1 square minus x2 square. Recalling what we'd found for g before, we found that g was the outlet pressure minus the inlet pressure divided by the length of the channel, okay, times 4 mu, so we have 4 mu L here, okay, times a square minus x1 square minus x2 square. Okay, that's V3. Right, and therefore V as a full vector is 0, 0 times this . Okay, so what we see here is that V has a parabolic profile across the inlet, across the channel. Right, it has that sort of a profile. Okay, it's parabolic. Right, along the E3 direction. Right, so this is V. Okay, it has a parabolic profile. Okay, for this particular case. Also note that what is typical in flows is that if you just start out a flow at one end of the channel, right, going to the other end, you typically have a pressure drop. Right, if you start out a flow here, you have a pressure drop at the other end, and this is a common experience. Okay, in any sort of flow, and the reason this comes about. Where do you think those losses in pressure come from? Right? If you're not maintaining the pressure, if you're not forcing the pressure, if you just send in something at some initial pressure and you get something, there is a tendency for the pressure to drop. We don't quite see it in this problem because we haven't extracted out those sorts of details, but the fact that you have a viscous flow is what causes pressure drops. Okay, because of the fact of viscosity, there are losses in the fluid. Okay, the work done by the stress upon the rate of deformation is not stored in a fluid. Right, there is no elastic mechanism to store that work done. Okay, and in fact, one can show, and we will show this at a later time, that all the work you do in a fluid, and especially in an incompressible fluid, is essentially dissipated away. Okay, and that is also related to the pressure drop, and that's why typically in terms of boundary conditions, we have this that difference. Okay, all right. Also note that in this case, if L was greater than A0, right, what you would have at every point in the flow would indeed be a velocity directed in the E3 direction. Okay, if you reverse that pressure gradient, you would have the velocity heading the other way as well. Okay, So there you see the effect of the pressure gradient and the velocity direction. Okay. All right, we'll stop here. That's an example of how we take the equations of continuum mechanics and solve a PDE. It's a very special method, of course, because we needed to solve this problem analytically rather than computationally, which is how we would solve more general problems, okay, with more general boundary conditions and fewer restrictions on the flow field or in terms of the constitutive assumptions. All right, we'll stop here.